Hello everyone. Today we're going to do some reverse engineering on a game that I really love, Hades. Quick reminder, this video is for educational purposes only. Please do not use this knowledge for harmful, unethical, or illegal activities. In this video, we will use only open source tools, the NSA tool Ghidra and one additional open source tool. Let's start by looking at the game files. At first, we can see folders named x64, x64vk, and x86. Since we're using a 64-bit machine, we'll focus on either x64 or x64vk. x64vk stands for Vulkan, which is an alternative to DirectX. Vulkan is known for better low-level control and performance in some cases. You can check some YouTube videos to compare. What really interests us here is the file called enginewin64.dll. This file contains most of the game logic. DLL stands for Dynamic Link Library. It's equivalent to a shared object or .so file on Linux. A DLL can be shared between multiple executables, and it allows developers to update or modify functionality without recompiling the entire program. In this video, we're going to modify this DLL and make Hades.exe load our modified version instead of the original one. Another important detail here is the PDB file, which is similar to a non-stripped binary on Linux. On Windows, debugging symbols are usually stored separately in PDB files. These files contain function names and variable names, and they make reverse engineering much easier. With a PDB file, the decompiled code becomes far more readable. Here is an example with and without a PDB file. Now, let's open the DLL in Ghidra. If you're not familiar with Ghidra, on the left, we have the program tree, which shows sections like .text, read-only data, and resources. We also have the symbol tree, where we can find functions and global variables. In the center, we have the disassembly view, and on the right, the decompiler, which generates pseudocode from the assembly. The first thing I usually do is open the defined strings window. Strings are extremely useful when analyzing a binary. I copied the strings into a text file and started searching for keywords. Since I was struggling with damage in the game, I searched for the word damage. The string damage multiplier immediately caught my attention. I copied its address in Ghidra and checked where it was being referenced. As we can see, it's used by several functions. After some analysis, I found where the default value was defined. The value is stored using the IEEE 754 format because assembly has no native floating point type. Using an online converter, we can see that this value corresponds to 1.0. We also see the instruction dwordputter address. This means we're accessing 4 bytes of memory, which matches the size of a float. Reminder, here's the difference between chord and dord, where byte for 1 byte, word for 2 bytes, dord for 4 bytes, and chord for 8 bytes. Now, let's convert 50.0 to IEEE 754 format and patch the instruction. Done. The value has been changed. We repeat the same process for the speed multiplier. I made a small mistake here. 50 was way too high for the speed multiplier, so I reverted the change and relaunched the game. As you can see, I can now one-shot all the enemies. Next, I wanted to prevent taking damage. After some research, I found a function called takeHit, which is called inside another function named applyImpact. Inside this function, we see a call to calc damage. My first idea was to replace the calculated damage value with 0. I also noticed another local variable that was initialized but never used, so I decided to reuse it. Here we see RBP minus 0x40. This refers to a local variable stored on the stack. I made a simple diagram showing how the stack works. From left to right, when we call the takeHit function, the return address is automatically pushed onto the stack. Then, execution jumps to the function body, where most functions start by pushing RBP and setting it to the current RSP value. The base pointer is then used as a reference to access local variables using offsets. Since we only need 4 bytes, we change the variable from a quad word to a D word and modify the value to 0. Then we replace the return value of calcDamage function with our variable. We use moveSS instead of move because we're moving floating point values. Unused bytes are replaced with NOP instructions to keep everything clean. After exporting the DLL, I noticed that this approach affects both damage dealt and damage received. So I looked for a better solution. A simpler approach is to modify the damage taken multiplier. This variable is only used when calculating received damage. After looking up where it is defined, we can change to 0, so every damage calculated will be multiplied by 0. Here we go. We can't take damage anymore. Next, I wanted to modify the game links, like the Discord and website links shown on the main menu. Let's copy our custom Discord link. These strings can be changed by patching the data section. One important thing to remember, we cannot exceed the original string length. We will do the same with changing the game official website with our new link. After applying the changes, the links are successfully updated. I think I copied the wrong link, but it's okay. Thanks to an open-source repository, we can extract the game assets. After extracting the GUI package, we gain access to all the graphical resources. I decided to modify the main character image on the home screen. I'm not very good at design, but it looks cool to me. We rebuild the package, replace the original files, and launch the game. As you can see, the new image is now visible. And that's it for this video. Thank you for watching, and see you next time.